So thank you again, and thank you to the university for taking the opportunity to allow me to present this technology. We started this company with the goal of trying to change the game, trying to find ways of improving technology nodes that people didn't think of, and so that's hence the title, "Breaking Through Silicon Barriers." And really, what's now becoming what people are telling, we're re-engineering, how silicon power devices are operating. And so, before I get into that, a bit of a background of the company. Actually, myself and the other founders have been at it for some time now. We started in 2015 with some initial university research projects that we were trying to use to get a signal. And in 2017, we achieved that milestone. We got a signal, and we created what we call SuperQ. And we funded the company. And since then, we demonstrated the technology on a 300-volt Schottky diode. And then we had COVID, and that set us back a bit. But then 2021, we demonstrated a 750-volt Schottky diode, and then we demonstrated a 650-volt MOSFET. And at that point, we felt that the technology was well enough to make a product. And so 2023, we started sampling our 200-volt MOSFET, and then last year, we finally released our 150-volt MOSFET, 200-volt MOSFETs. This year, we'll start sampling our 650-volt MOSFETs, and we're starting to work on 650-volt IGBTs. And with that, I'll just kind of jump into probably a more fundamental question about, what is it that, what compelled us to invest in silicon? And particularly those of you that are in power, it's well known that, there's been a lot of inroads made with silicon carbide and GaN, and a lot of talk about that silicon is dead, and, the future in power semiconductors was going to be silicon carbide and GaN. So, this is back in 2015. What compelled us to go off and do so? And one of the driving forces was cost performance. And I'll get into those details in later. But I wanted to start with this because this kind of really sets the background of one of the driving decision making in power devices, and that is the resistance. And most specifically is the resistance per unit area, which they call RSP. And so just bear with me as I walk through this timeline. So on the x-axis is calendar year, and on the y-axis is resistance per unit area. And back in the 80s to the early 90s, International Rectifier really was the leader in power devices. In Pacific, what I'm highlighting is 650-volt MOSFETs. And so they had, the HEXFET technology, which had, basically leading RSPs or resistance per unit areas at the time, and really dominated the market until the mid-90s when a company by the name of Infineon came out with a technology called superjunction, and it really made a significant drop in the resistance per unit area. So, when people talk about resistance per unit area, that also ties to the die size. Like any semiconductor technology, as technologies evolve, die sizes get smaller, which reduces the overall cost, or for the same die size, you can improve the performance. So in MOSFETs, the lower the resistance per unit area, the more transistors you can cram in, the lower the resistance or smaller die size. But anyway, point being that technology was a step function change from the HEXFET era. And so, Infineon really spearheaded this technology. You'll hear me talk about Infineon throughout the program, mainly because there's no debate. They are the leader when it comes to power semiconductors. And so when you're a startup company or you're any competitor, you always want to use the best, or you always want to compare yourself to the best in the industry. And so they're definitely the leaders. So and they're the bar. So if you can outperform them, then you're in a good position. So you'll hear me talk about them a lot. But anyway, so they came out with this technology, which then eventually led to subsequent generational improvements. And they led the industry when it came to this one specific parameter.
Mhm.
But over time, the technology actually got more expensive and the improvements started to slow down. And, in 2010-ish, 2008 to 2020, 12-ish, the emergence of GaN and silicon carbide started to become realizable. These technologies started to look like they were going to be practical for manufacturability. And the parameter that they focused on was resistance per unit area. And so you can see, similar to what Infineon did at the time, these technologies look like a step function improvement over the superjunction technology at the time. So huge investments went into trying to productize GaN and silicon carbide. And That really led to this whole campaign that silicon is dead and that silicon is starting to reach its limits. And so almost the entire industry had some form of investment into GaN or silicon carbide in the orders of hundreds of millions of dollars, and in the case of Wolfspeed, billions of dollars. But rightfully so, because the industry saw this slowing trend and thought, okay, well, there's got to be a next generation platform that's going to become the next era. But meanwhile, Infineon continued to drive improvements in that technology, and until mid 2020, you started to see some really slow progression in this RSP, or this resistance per unit area. Up until they got to where they're at, I guess last year they released their latest and greatest silicon-based super junction technology called CM8, and a pretty significant reduction in the resistance per unit area. Um, the only drawback is that they significantly increased the cost. And at the time, like any technologies, GaN and silicon carbide was very expensive to manufacture. The quality was very poor. People had to reinvent how to do reliability testing because they were doing new materials. But the thought is, over time, things will get cheaper, and that's generally true for most technologies. But that's where Infineon landed with this their latest super junction, and where GaN is today, for the most part, it's about the same when it comes to this one specific parameter. Then there's the switching loss, and then there's other system level parameters that I'll get into in a bit. But it really just didn't show much of a, or at least the GaN technology has not really shown much of a significant improvement when it comes to resistance per unit area over what has been recently released. And since then, silicon carbide really has improved itself, at least the standard MOSFETs. I'm not talking JFETs. JFETs, I think, sit down somewhere down here.
Mm-hmm.
But the magnitude of improvements that was once there when this technology first came out is not there anymore. And the cost to manufacture these technologies hasn't really come down to a level that the industry expected. Hence why companies like Wolfspeed had to reassess how they spend money on these technologies. But um, we decided that we were not going to go down that path. We were going to create a technology which lands right about in the middle of the pack with for 650 volts for GaN and silicon carbide, but more importantly, balance cost performance. And why this is critical for power is because power really is it's a necessary evil for the things and the gadgets we all love as consumers. Your phones, your computers, AI, whatever it may be. Power is not like it's not the selling feature. It's the necessary component to deliver the function, which is what what we need in the phone function or the laptop or whatever it may be. And so the performance and the cost of that technology and power has to be well balanced. There's no point in coming to the table with the world's most highest performance MOSFET if the cost is too high for the industry to adopt. And the reverse is true. There's no point in having the cheapest MOSFET in the world if it doesn't deliver in performance. Over my 30 years of working in the industry, the industry could probably bear 10 to 20% cost performance um, what is it, premium over the current solution in order to gain that benefit. But if you're two, three, four times more expensive, what the industry can bear, you're just not going to get adopted. And so that was one of the pillars that we wanted to build on, is to make a semiconductor that was meeting that cost performance metric. But not only that, it was not going to be a structure that was going to be a one trick pony, meaning that it's just that and there was no path to improve. Based on our roadmap, we see a path to almost 100 millionths millimeter squared, meaning that this technology that we developed from a resistance per unit area, we believe will keep up the pace of the improvements seen by the wide bandgap technologies. For that one metric, we think that we're in a good position. But more importantly, technologies always find ways to reinvent themselves. What I have here are the theoretical material limits of what was used to drive that campaign of the silicon limit is this number, which was driven by this hex FET generation. The superjunction what they call a symmetrical superconductor structure, which is basically the core of Infineon's technology. I think this number could get lower. And then you have the lower limits of silicon carbide and GaN, which are 15 and 5.5. So if you look at these numbers and you compare it to being in the hundreds to thousands, you think, wow, the roadmap or the opportunity is wide. But then if you look at what we can do with our technology, the theoretical limits is down at 22. And so what I'm trying to illustrate here is that all technologies, no matter where they're at today, there's always ways to find ways to reinvent themselves. And so I would not bet against silicon. I would not bet against silicon carbide either or again. I think that, to say that one technology is going to disappear because the other one at the time is getting slightly better performance is just not true. I think they all find ways to mathematically find a performance metric that they can improve on. And all of these, the references are down here at the left-hand side bottom. You can go read into, what are the true limits of those technology nodes. But for today, this is where the industry's sitting, and this is the path that we think we're going to take. And so I emphasize that one metric, the resistance, because that's really core to a power MOSFET. On resistance matter, but further, switching losses matter. And so we wanted to create a technology that also reduced the switching losses, not only focused on arm resistance, and I'll touch on that topic as we get down in the presentation. But equally as important and not widely talked about is the robustness and the ruggedness of the structure. Those of you that are in power systems know that when things fail in power, it's quite catastrophic. And one of the first things to fail are the MOSFETs, regardless what the problem is, even if it's not related to the MOSFET. MOSFETs become the fuse of the system, and then when they fail catastrophically. Next thing to fail are capacitors, electrolytic capacitors. If you're ever blown one up in a lab, it's quite a quite a show. But there's an expectation that these devices have to be robust. They have to survive avalanche. They have to have surge current capability. And so to only improve an RDS(on) is to be very narrow focused. If you're going to develop a technology, you have to focus on all the metrics, inclusive of robustness and what I said earlier, making sure the technology is well balanced from cost performance. Again, the industry will just not adopt you if you're 2-3x more expensive than what the industry can bear. So those are the 4 pillars that we built on. And so I'll jump into kind of how the on resistance matters, or how we did, how RDS(on) is manifested in the structures, and how we are different from the rest of the industry. And so I'll go back to the 3 basic technologies today: the HEXFET technology, the superjunction technology, and then our technology. And this is a cross-sectional view of the device. For those of you that are not device physics or don't understand the structure, bear with me. I'll try to simplify the flow and how this thing works. But one thing to know, in power applications, most or literally all switching applications and almost all power, MOSFETs are really looked as a switch. You want to be able to turn on the switch with little to no resistance. Basically, you want zero resistance. And when you turn off the switch, you want it to block infinite voltage. That is really the 2 core fundamental things that a MOSFET has to do: block infinite voltage and have no on resistance. And the way we do that is we really have the industry has normalized around what they call vertical power devices. At least most of the good power devices are vertical. And what that means is that if you can visualize a silicon wafer, or any wafer for that matter, the backside of the wafer is a drain terminal in a MOSFET, and the top side is the source. And so like in the drawing, this would be the back side of the wafer, this would be the front side of the wafer. And the way current flows is top to bottom, right? Top to bottom or bottom to top, depends on which way you want to view it. But it's a vertical flow of current. And the way the device blocks is vertically. You drop the voltage across this entire material to be able to block. And so those are the fundamental functions of the device itself. And back in the HEXFET era, you can see, this is the N epitaxial region, the P plus, or the P body region, and the N plus contact, and here's the gate. And the fundamentals of a MOSFET: you enhance the gate, it inverts this region, and current conducts through this region and then goes through what they call the epitaxial. Power devices, and particularly higher voltage devices, rely on this salmon-looking region for blocking. And but unfortunately, that region is in series with the channel of the device. So when it comes to the core MOSFET structure, the mobility through the channel matters from a resistance from on resistance. But when it gets to higher voltage devices, 100 volts, 200 volts, 600 volts, 1200 volts, most of the resistivity is in this bulk region, which is being used to block the voltage. And so you can see back in the HEXFET day, as you enhance the channel, eventually current just basically flooded the drift or the epitaxial region and flowed out through the drain terminal. And at that point, you're really following geometric features of the epitaxial, meaning that the thinner and the higher dope the material, the lower the on resistance. It just follows those basic fundamentals like any resistance material follows. The issue with this structure is that when it came to leveraging this material to block voltage, as you increase the voltage, the on resistance of this material or the resistivity of the material had to increase at a 2.5 exponent rate, meaning that if you have a 100-volt device and you went to 400 volts, it's going to the on resistance is going to increase by more than 4x. And so a lot of those one-dimensional limit lines you see on paper about silicon and why it was time to reinvest are based on these structures. And then when Infineon came out with superjunction, which is really what they call a resurf structure, it's a reduced electric surface field structure. And at the core, what they're doing is they're carving out half the silicon and putting these P plus pillars. And what these P plus pillars do is they charge compensate this end drift region. And so now what this region looks like is what we call is a silicon mesa. So it's got that shape of a mesa. And so really all the current now is only flowing through this region. And the reason is you need these P regions to charge compensate the drift. So every hole or every hole carrier in this P region has to equal the N or the electron or the N carrier in the drift region. And so it's a combination of these two P pillars that allows this region to decharge compensate. And as you reverse bias, it pulls carriers away. The holes move into the source contact. The electrons push their way into the drain contact, and you end up having intrinsic silicon. A lot of details. If you want to learn about it, go online. There's more equations behind it that I'm simplifying here. But fundamentally, what it does, it nicely creates a uniform electric field top to bottom. The equipotential lines get distributed evenly laterally, and so allows you to block in a more efficient way compared to this structure. To where now the thickness here, the amount of epitaxial you need to block, now grows at a near linear rate, or the on resistance grows at a near linear rate of the blocking voltage. And so therefore, if you have 100 volt and you go to 200 volts, you're really only increasing the on resistance by 2 in theory. It's a little bit higher than that, but more importantly, a parameter that we look into or that we look as a way to gauge the effectiveness of the structure is the volts per micron that you're dropping, meaning how thick is this epitaxial in terms of micrometers, and how much voltage you're dropping across that when you're reverse bias. And early on when this superjunction structure came out, it was in the 13 to 15 volts per micron, and they've improved a little bit since then. But that blocking capability, along with the charge compensation that occurs, is what allowed it to really make a step function improvement in RDS(on) compared to, excuse me, the HEXFET. Then came our technology. Fundamentally, at the core, we're also charge compensating a drift, but we're not relying on a P implant or P column as it is in here in this symmetrical superjunction structure. We're relying on what we call a charge layer or charge dielectric, and it's very, very thin. And as a matter of fact, it allows us to then now revert back to the HEXFET days where we had these very wide conduction regions and these very narrow charge compensation regions. So these red lines that are unparalleled to the mesa are what create the same function, that charge compensation function that you saw with this P plus. We're only doing it in a very smaller area. So you can see geometrically, we can have high dopant and very wide mesas to improve the conductivity and therefore reduce the on resistance. A second order benefit is that we don't need to have, you see here, these guys have this little buffer layer, and they're doing that for robustness purposes. We don't need it, so that means that we could have a thinner epitaxial layer. And then finally, our ability to block voltage around 18 or 19 volts to 20 volts per micron, improving on what was being done back then. So all in all, that allows us to make a thinner layer, reduce the RDS(on), open up the mesa width so that the conductivity can just spread uniformly and get to the drain terminal without having the impact of on resistance. And so there's a white paper on our website. If you go, you can download it. It talks a bit more detail about this comparison point on our webpage. And so what I'm showing here are actual structures. So it's nice to be able to show cartoon drawings, but these are also cross sections of that concept, the super junction structure here from Infineon, and this is our structure here. And so you can see these lighter gray areas is that conduction area, that mesa area, and these darker gray areas are those P pillars that charge composite. And you can see overall they have these columns, the PN columns. And the way you manufacture that, and with the Infineon's latest and greatest, it's an elegant technology. It's beautiful, especially taking into account the way they manufacture it. But it's very time consuming to process to a point where it's roughly about 136 days to manufacture. And I'll get into that those details in a bit. Compared to our technology, it's about 44 days. More importantly, you can see this is our mesa here. The darker gray lines is that charge compensation. This structure showing a 1 micron mesa with a 1.1 micron trench. This was our first prototypes. Actually, the 650 volt MOSFET we'll be releasing today actually is going to increase this to 4 microns and with a 1 micron trench, meaning that we will be utilizing about 80% of the conduction area versus this structure here is only utilizing 50% of the construction area. So that's one deficiency. But then this gets into the manufacturability for how to build that traditional super junction structure. This gets into how fabs operate. You start off with epitaxial, and you implant a phosphorus species and a boron species. So phosphorus being an N type and boron being P type. And then you mask it, you implant phosphorus, you mask it again, you implant boron. And then you grow another layer, then you mask it again, you implant, mask, and you do that multiple times until you get to the final structure, and then you drive it in. Well, if you ever get a chance to work in a wafer fab, the number of masks matter, meaning meaning that it takes longer to process, meaning that the cost to manufacture is higher. Typically, vertical power MOSFETs or vertical power devices are in the range of 8 to 12 mask steps. That has traditionally been the target for these power devices to balance that cost performance metric. Today, our estimates is that the latest and greatest super junction structure by Infineon is around 28 to 32 mask steps, which makes it very expensive. Compared to what we're doing today, our technology starts with bulk epi. We etch a trench, we line it with this charged dielectric, which I'll talk about in a bit, and then we fill it with dielectric. That's it. And so that's how we balance that cost performance, meaning that we manufacture a product that gives the same performance with a higher manufacturability throughput and lower costs. Back to the structures. Again, this real devices, these are the IV curves that we use to fund the company. This is a Schottky diode that we first built with the technology blocking up to 380 volts. This is a 650 volt Schottky diode that we used with this structure to prove that the same core SuperQ technology can block voltage up to 650 volts. And so it's real, manufacturable, and getting into more of the details of, well, what is SuperQ? I talked about those PN column and that charge compensation of the drift. Fundamentally, the way we block that method is similar, meaning that we charge compensate the drift and then dispel carriers and we block voltage. The difference is that, as I said earlier, we're relying on a charged dielectric that we deposit on the sidewalls of our mesa. So I have these two structures here. This is a view, and for simplicity purposes, what's drawn here is a PN diode. So N plus at the bottom, P plus at the top. And this is in a zero bias state. So basically how it starts off before you reverse bias. And so the sidewall, this is just for illustrative purposes, the insulator. It's a charged dielectric with negative charge. And when you put that charged dielectric on the sidewall, it'll displace the electrons adjacent to it because charge wants to be balanced. If you have a negative charge, it naturally wants to draw a positively charged atom or particle so that it could balance itself. So what ends up happening is analogous to the inversion layer of a MOSFET or a MOSCAP, for those of you that are device physics. That is that it displaces the electrons, it pushes them to the N plus contact, it pulls in holes, and it inverts the region. So now we end up having, you have negative charge dielectric, properly balanced by the accumulated holes on the sidewall, and the same is true on the other end. And so now the device is in a balanced state before you put reverse bias on the structure, and this becomes our main. As you start to reverse bias, the electric field imposes itself on the structure. Electrons will find their way to the N plus contact. Holes will be dispelled into the P plus contact. And as you reverse bias the device, you eventually deplete the drift of carriers to where now you've ionized the atoms, and those ionized atoms are charge balanced with the negative charge found in the dielectric. So fundamentally, similar to superjunction in a sense that you have to charge compensate the drift. At the core, though, we do it by relying on a negative fixed charge in a dielectric. And so this method of charge compensate, actually, there was a paper that came out of this university back in 2008, similar to what was presented in that. And now I've seen a whole bunch of other papers on this topic, which is good. Helps drive the innovation on this methodology. But point being that it fundamentally it does the same function, which is you're redistributing the equipotentializing, you're manipulating the electric field so that you can displace carriers, create an intrinsic silicon, and then allow you to block voltage. So bit of a mouthful, but if you want to learn more, we actually submitted a paper to ISPSD this year. So if you get a chance to go out there, Dr. Phil Rutter, who one of our VP of Research and Development, submitted the paper. It's been accepted. He's going to present it. He'll talk in more detail about what it delivers from an RSP. These are some of the drawings from there, which I'll touch on lightly. But if you get a chance, certainly go up to him and say hello and ask him any questions you want to ask him. But the paper specifically focused on 150 volt to 200 volt MOSFETs. And part of the reason is these are the products that we have out there today, released and being designed in with customers. But also, we want to illustrate the fact that, what you'll find in the subsequent slide is that the technology used for 650 volts MOSFETs and to do blocking, that blocking function, is actually different than is done down at 200 volts and 150 volts for everyone else. And that blocking function down to 60, 40, and 30 volts is actually also different, meaning that the industry has found ways to create technology nodes that are very specific for a small voltage range. Our technology actually works down to 60 volts, and I've modeled it up to 1200 volts, and it works every time, meaning our one platform can now deliver products that span a very wide range of voltage class MOSFETs without having to fundamentally change the core structure. And I'll show you how the industry has done that for this device in the next slide. But showing here that with 150 volt MOSFETs, we were in a leadership position against Infineon. Our leadership position is not as large as it is with higher voltage devices, but nevertheless, we're able to show with our first generation structure to be ahead of Infineon's sixth generation structure. At this stage, to me, we're all within the same realm of RSPs. So depends on which way the wind blows. You can debate one is better than the other, but we're really proud with this technology being able to be that level of performance. We think that we're ahead. But then if you look at 200 volts, that's where our separation really starts to get greater. This first generation platform that we've developed was really more intended for 200 volts and greater. Our next generation platform is going to go off and build on this and then hopefully put a larger leadership position. But you can see that resistance per unit area separation gets greater at 200 volts. That gets significantly greater at 300 volts, 400 volts, and then, better at 600 volts. And those of you that are in power and have built power systems, and if you ever needed a 300 volt MOSFET, you'll find that there's nothing that's very good in low on resistance. And part of the reason is no one's developed a technology that can deliver MOSFETs that are really good at 200 volts or 400 volts or 300 volts. Well, we have that now. You're actually starting to see some silicon carbide MOSFETs being developed at 400 volts. Our technology rivals those MOSFET classes. So anyway, more about that at ISPSD. Read the paper; it'll be published in IEEE. And this is the structure; it's real. This is our mesa. Here's that trench, and then there's that dielectric around the mesa, and then this black area is really just a void, not used for conductivity. So, building on that 200-volt MOSFET structure, this is that structure that I talked about that is now different than the classical superjunction that I showed at the onset. This still relies on charge compensation or resurf to try to deplete the drift region, but it does it with a capacitive coupled field plate. So this is actually metal, and this is an oxide. And what it does, it capacity couples the drift, it depletes the drift region, and it blocks. And so all the current has to flow through this region, and then they add this lower high resistance or lower doped higher resistance buffer layer to help improve the blocking voltage. And so this was the leader back in 2011, and you can see their mesa width is about 1.8 microns wide. And this region, which is used at that blocking function, is about 2.5 microns wide. So actually, they're less than 50% utilization of the silicon area. And then in 2024, they released their 6th generation technology. Again, this is Infineon. And they went from having a 1.8 micron mesa to 1.2 micron mesa. And so clearly, they were able to improve the resistance per unit area by heavily doping this area, but you can clearly see geometrically they're starting to reach these manufacturability limits. And then once again, this is that same region that's used for blocking, not used for conduction. This is a field plate. And so all the current's got to funnel through this region and then go through this higher resistivity material. Our technology, taking that 650 volt MOSFET structure, bringing it down to 200 volts. Here's what you get. There's our 3 micron mesa with a 1 micron trench, and you can see, our mesas are wider. We're actually going into the substrate, so we don't have to. We don't rely on a high resistive material underneath the structure, and that allows us to have this leadership position in on resistance. But more importantly, you look at the structure and you think, okay, where are you going to go next? Half a micron, a quarter micron? You look at this is only about 28% of the conduction area is being used, whereas the rest of it is being used to block. It just becomes a structure that follows that we're starting to run out of RSP improvement curves. And hence why technologies like that seem very attractive, because they have a longer roadmap when it came to the core fundamental structure and how you manufacture it. But with SuperQ, we've gone back and we widened this mesa, and we really are limited by how narrow we can make this trench. Our goal is to try to make this region that only is used for blocking as narrow as possible. So with that said, that kind of segue into the capacitive or the switching characteristic of these devices. And this is kind of a preview of that CV curve. You heard me talk about pinch-off voltage, or when these things deplete, they deplete laterally, and then a region becomes intrinsic, and then all of a sudden you reach a pinch-off and you start blocking voltage. The way that manifests itself in the characteristics of the MOSFETs is when you look at the drain to source capacitance, or what they call the COSS, as a function of reverse bias, you'll see that the semiconductor material or the semiconductor starts with very high capacitance, and as reverse bias reaches abrupt change in capacitance, that is that pinch-off point where this region becomes completely depleted or intrinsic, and you start to block voltage uniformly across the drift. All semiconductors have some form of change of capacitance versus reverse bias or biasing when it comes to this behavior, whether it's GaN, silicon carbide. The question is the magnitude. And so these silicon-based structures, they have it here, not as abrupt. Our technology had a pretty significant abrupt change. Actually, you look at where we start at 9 nanofarads, and we end up at 20-ish, 30-ish picofarads. That's multiple orders of magnitude, a drop in capacitance. And so when you take off your device hat, or you look at it as a device designer, you're saying, well, what's the impact? Well, you have to put on your device, or your system designer, which is, I've designed many systems. You think, well, is that a good thing or a bad thing? And me personally, I saw this as a system in the application could be very beneficial, and I'll show why. Gets into the switching topic, right? So it's one thing to talk about resistance per unit area. To make a well-rounded structure or a well-rounded power device, you also have to address switching losses. And so the benefit of that shape of that curve, it actually really reduces your switching loss characteristics, and particularly the I times V loss, or what they call the hard switching loss. You guys that are system designers, certainly RDS(on) losses matter, but at some fundamental frequency, your switching losses start to become a dominant contributor to the overall thermal management of the system. And that's really just the I times V product overlap that these devices are requested to see in the system. A lot of it driven by the fact that they're driving inductive loads. And so traditionally, that parameter was driven or measured based on a normalized or an idealized behavior. That is that, bear with me here. Typically measured in what they call a double pulse tester, and it's really just a MOSFET with an inductor and a diode clamp, which at the core simulates power, switching power supplies, motor drives, uh, audio amplifiers, all these applications. You're driving an inductive load. So this double pulse tester the industry has used as ways to mimic those applications and mimic this I times V energy loss or turn on switching loss. And so what was believed was an idealized rising of the when you're turning on the MOSFET, the idealized rising of the current and linear change of voltage is no longer true for especially research devices, and it's very much not true for our technology. The real volts and currents you can see rise at a nonlinear rate and then become linear. And the switching loss is really the area of the I times V product, the area of that curve. And you can see that our switching loss is actually quite a lot lower than actually would be predicted with traditional methods of measurement. And so therefore, we actually went off and wrote a paper or an app note on the topic. You can go to our website and download it. But what we're trying to highlight in this paper is that we need to redefine how we specify parameters in our data sheet to be able to predict switching loss. I know a lot of data sheets these days are putting, in particular silicon carbide, are putting down E on and E off. That is the energy loss at turn on and the energy loss at turn off. But unfortunately, that only works for that very specific set of conditions that they give you in the data sheet, meaning that gate driver, that gate resistance, that current, that voltage. If you want to be able to predict it for different voltages or different currents, you really need to know that time element. And so there's a parameter in MOSFET data sheets that some people do put it in, some people don't. It's called Q switch. And that Q switch parameter is really that time element that you can use to predict your switching loss. Like I said, more details in that app note. I don't want to spend too much time on it, but the fundamental equation builds on trying to calculate the switching energy, which leads to switching loss. And then there's that equation where you just take that charge element that is associated with that time, and you divide it by your gate current, which you know ahead of time by knowing your gate resistor, and then you can calculate whatever your switching loss is going to be. If you get a chance to go to APEC this year, there's going to be a poster session on this topic, so please just stop by and take a look. And I'm going to present a paper not on this topic, but on switching losses in general at APEC. So if you get a chance to go out there, please stop by, say hello, and I'll be more than happy to chit chat about switching losses. But so there's that switch loss element. Then there's, okay, what about the amount of energy you store in that capacitance itself? There's that CV curve here. And, when it comes to that parameter, what matters there is the stored energy, or what we call EOSS, which is really just the integration of the CV curve, really the integration of the charge over voltage, which gives you the energy. And what I'm comparing here are basically three MOSFETs of the same RDS(on), right? I don't want to just show you curves that are irrelevant. I want to normalize it so that for the same RDS(on), you can do a direct comparison of the capacitance curve. And sure enough, here we are with very high capacitance, and we drop quite sharply, and then we end up with very low capacitance. Here's the same Infineon Optima 6, similar RDS(on). They start midway, and they come down, and they actually end up lower than the third curve, which is an EPC device. Starts low, has that change. You can see, like I said, all technologies have some change of capacitance, and then flans out. So what does that mean, right? I mean, is this a good thing or a bad thing? Well, from an EOSS perspective, it's actually a very good thing because, again, once you do the mathematics and you look at the amount of energy stored in the application or in that capacitance, you can see at low reverse bias at 10 volts, for example, our stored energy is higher than the other two MOSFETs. But all three MOSFETs here are rated for 150 volts, meaning that you're not only going to bias them at 10 volts, you're likely going to bias them around 90 to 100 volts. And you see that our stored energy doesn't rise as fast as the other two devices. You can see the Infineon device really just takes off when it comes to stored energy. And then the GaN device actually starts to run, become I guess, second place when it comes to this curve. So, if you look at our stored energy compared to GaN, we're actually leading. Um, and so to put it all together, um, I have a couple slides that, like I said, are core to the APIC paper that's going to be presented. We took a boost converter. And a boost converter at 375 watts, we set the output voltage to 75 volts, running at 300 kilohertz. We put a silicon carbide Schottky diode. For those of you who know boost converters, there's a rectifier diode on the output. And we intentionally put a silicon carbide diode, which is over designed because we didn't want to use, or we didn't want the reverse recovery to become an influence on how the operation of the platform. We wanted to try to normalize everything else and only focus on the MOSFET itself and the switching characteristics of the MOSFET. So, we took those same three MOSFETs and we redesigned this board to be the same, as close as possible. We used the same gate driver. We adjusted the gate resistor. We adjusted the gate voltage for the GaN device because the GaN device could only be driven with 5 volts. If you go to 6 or greater, you break the device. And we adjusted the gate drive voltage on the silicon MOSFET so that the RDS(on) would be the same for all three. And because of the differences in the gate structures and, that's going to drive differences in gate drive loss. So in this analysis, we didn't consider it. There is absolutely no reason why you cannot make a silicon MOSFET have a 6-volt rated gate and have the same gate drive losses. So we set that aside and only focus on the core switching loss while normalizing the conduction losses. And so if you take those fundamental equations that I presented earlier and you do the math under these conditions, 75 volts, which is a volt stress that the MOSFETs are going to see, 5 amps, 300 kilohertz. You start off with the I times V loss, that E on E off, switching loss. The same three MOSFETs, the GaN in blue, Infineon in orange, and then us in red. You do the math. The EPC has, on paper, at least better switching losses that mathematically than we do. And then we're in second place, and then the silicon device is obviously starting to take off. From an EOSS loss, you can see that now we are in the leadership position. The GaN is slightly higher in loss than us, and then the Infineon silicon device. And then we add them all up together, you can see as a skyscraper is the silicon device, and then mathematically the EPC device is in a leadership position, and then we're just close next to it when it comes to a switch and loss. So if you do the math of taking this loss or this loss minus that or the differential, mathematically we're saying that EPC is going to be ahead of us by about a quarter watt, but we're going to be ahead of Infineon's latest greatest by a 1 3/4 watt. That's the theory, or at least that's the expectation. What happens when you actually measure it? Well, here are the measured results. This is delta power loss versus current. So again, looking at their power loss minus us. And so as expected, the Infineon at light load behaved as we expected it. And then when you got to full load, the difference in power loss approached what we expected. What we did not expect is what happened with the GaN. At light load, it was all EOSS related losses, which made sense, and we were supposed to have an advantage. But as we increased the current, the part started running away on us, and actually it failed on us multiple times. We built 5 boards, 5 times we fell apart. I don't know what we did wrong. We had the heat sink that they recommended, at least from a size. This is from their data sheet. We had 100 millimeter squared on a 50 millimeter squared device. We looked at the voltages, both drain and current and gate. We weren't violating anything, so I'm not sure what we're doing. I've heard rumors that GaN has a hard time working with hard switching applications, and that you really want to focus on soft switching applications, which is counterintuitive to me because GaN, you want it to be you want to leverage a low charge for that application. But nevertheless, there must have been something that we were doing wrong. We couldn't get it to the current, but if you look at the measured differential loss, this is what we predicted. The measured loss difference in the silicon device was Infineon was about 1.5 watts versus 1 3/4. We're pretty close. I think I know why this came in lower, and it has to do with what we assumed was a gate current. And then obviously we couldn't measure the EPC part because it never made it to 5 amps. So overall, what I was telling you earlier about the mathematics to predict your losses, fairly agree with the predictions or the measured results. So excited about that. That's how we're addressing switching losses. Then the last final parameter I want to address is that ruggedness and robustness, right? I talked about how that is so important, and particularly because what I just showed earlier, right? These things can fail quite dramatically. And so I'll start off by just highlighting our technology is fully qualified. We actually take it beyond the JEDEC standards and go into 3,000 hours and whatnot, because we want to prove that and show the industry that it's a brand new technology, but we're building on the fundamentals of silicon, that it has very well established reliability and qualification standards. Whereas the wide bandgap technologies, they had to kind of figure out how to properly stress the devices to really create an environment that gives you these so-called accelerated results or predictions of when the failure mode is. So this is just, for us was just more tactical. And then we also been qualified for automotive grade standards. So um, in line with what we expected by the fact that we're building on a silicon structure that has this fundamental history with good quality and manufacturability. But we also did not want to make a MOSFET that was only good at blocking voltage or only good at low RDS on. We want to make sure that you can have good UIS capability. GaN, unfortunately, you cannot put that MOSFET into avalanche because it'll break. And I recall early on that the UIS capability of silicon carbide had issues because of some of the defectivities found in the epitaxial. So UIS is a must. Avalanche robustness, if you ever are designing a system and you look at the MOSFET, and if they do not put avalanche rating in that data sheet, stay away from that MOSFET. Trust me, you do not want to use it. You want to make sure the MOSFET has some kind of UIS rating. The other thing you want to look at is the surge current capability or the pulse current ratings. And so, you know very well the system designers, when systems fail, currents go through the roof and things start blowing up. So you want to make sure your MOSFETs can withstand that. And so we devised this circuit where we were basically just creating an ideal current source that just dumps a whole bunch of current into the MOSFET. And so system designers, you create protection features in your design that monitor the current. And when the current gets too high, you want to be able to turn off the system quickly before anything blows up. And the guy that's turning off is the MOSFET. So when your MOSFET turns off, it has to survive that event. And so that's what this test is showing, is just showing or is trying to demonstrate what happens when you turn off the MOSFET in a very high current atmosphere. Very common in motor drive and in battery applications. When the motor stalls or when you short the terminals of the battery, you get this high current events, and the MOSFET is expected to block and turn off. And so once again, we're comparing ourselves against Infineon because they're the leader. We ran this test. They showed about 584 amps of capability before they failed. We tested our same MOSFET with us at the same RDS on. We got to about 800 amps, which there's going to be a paper in Bodos next year that talks a bit more about this. So if you want more details, but we were proud to show that we were able to increase the current capability. And part of that has to do with, I know we're running out of time here, our core structure. Remember, I showed you earlier that field plated structure. Well, that device that we tested from a surge current perspective was this structure. And there you go again. You have this very narrow mesa compared to our structure with a very wide mesa. And the laws or the thermal dissipation density. Part of it is driven by the thermal mass of the material, thermal conductivity away from the junction. So everything can be the same. Something with more thermal mass is going to be thermally better. And that's kind of showing here in this performance curve. This is the surge current as a function of RDS on. We're actually going in the higher increasing performance, whereas that technology node went from here to here. When you increase or you decrease the RDS on, they actually decrease their current capability. So very excited to show that we've developed a platform that also is very robust, along with meeting the standard reliability, qualification, and avalanche ratings needed for the application. So, in summary, silicon-based power semiconductors will continue to innovate and improve performance. The lesson learned here is to the industry is don't bet against silicon, But this does not mean that GaN and silicon carbide won't reinvent themselves. I think all technologies find ways to reinvent themselves. I tell people that work for me, we're engineers, we're paid to solve problems. So engineers will find ways to solve problems with whatever technology is put in front of them, especially if they have an idea or a means to improve on that main technology. So when people tell you that can't be done, well, it usually can't be. Famous quote: "You can't. It usually can't be done until someone figures out a way to do it." That's why we're engineers. And so SuperQ, we wanted to build a technology that addresses all pillars: conduction losses, switching losses, balancing cost and performance, reliable and robustness. So for you guys that are entrepreneurs, if you have a technology that touches those three elements, you've got something special. Go off and build it and bring it to the industry. And with that, I say thank you, and hopefully I pasted in the right translation and I didn't offend anybody. So thank you again.
Yes, it's now open to questions. People can either raise their hands or type their question in the chat box, so we can go through that. Um, but in the meantime, David, there were some questions that people had shared during registration, so I'll go through those now. So I guess there was a question. How did you reinvent the architecture of silicon devices? What was your first step in thinking about it?
Well, it was what I showed. That's why I started with that timeline of RSP. It was
Yeah.
this madness of silicon is dead, and I saw the industry pump hundreds of millions of dollars and make these claims that silicon was going to disappear by 2015. And 2015 came, and they said it's going to happen by 2020. And 2020 came, and it's going to happen by 2025, and now nobody knows. So it's just it was that idea that we had to create a technology that not only brought performance, but brought balance of cost and performance while providing robustness. So, and early on, those wide bandgap technologies were delivering on performance, but not on cost and not on robustness. So there was a gap.
Yeah. No, that is true. I think that is a comment that we see that, definitely there's a lot of progress happening on wide band gaps, but I think the researchers working on silicon continue to find innovative ways of staying in the game very well. So,
Right. Correct.
how do you see SuperQ evolving in the next 5 years, especially with the rapid growth of AI and advanced computing technologies?
I think the need for power is going to accelerate, and certainly AI is going to be a good way to assist in the design process. But you still need engineers to help kind of navigate through some of the responses to develop a good technology. But I think for power in general, it's a good thing. It's kind of a scary time because those of you that are on power, you'll see that the power requirements for AI are going through the roof to a point where they may not be sustainable. And so there's got to be some kind of correction or some kind, in my opinion, some kind of adjustment because the industry can't keep up with the power demands. But the requirement for power semiconductors will always be there. We'll always find ways to make more efficient power semiconductors. And we believe SuperQ is going to be there in all of it. At least that's our expectation.
Then there is another one which I think you've somewhat answered, but I'll just ask, with the rapid growth of wide bandgap semiconductors, what is the long-term future of advanced silicon power devices, and how does SuperQ help with innovation?
Well, I think
Yeah.
that if we can continue to address those pillars, the switching loss, the conduction loss, the robustness, and the cost performance, we have a long roadmap. We honestly, I tell people that our goal, and sorry for you Infineon fans, we want to be the next Infineon, and with SuperQ we can do that. But more importantly, the core of SuperQ is the core of our IP is charge compensation,
Yeah.
meaning that there's already some papers out of this university that are looking at that same concept for wide bandgap technology, and particularly silicon carbide. And so if you apply our technology on silicon carbide, it actually does the same thing. It improves the performance. So we're looking at investing in technologies that deliver that balance. It doesn't matter if it's silicon carbide or silicon or GaN or it just for now we think for the next 15 to 20 years it's still going to continue to be silicon. By then the wide bandgap technologies, hopefully the quality, the reliability, and the cost will be there.
Cost.
then we'll pivot to that technology node. I'm not going to bet against, particularly silicon carbide. If I was a betting man, I would bet a silicon carbide, not GaN, but that's a different story. But yeah, technologies find ways to reinvent themselves and become a commercializable product.
Yeah. Let me just take some of these questions that are coming online, and then I'll get back to a couple from before.
Okay.
So, question from Mohit: how do you comment about the thermal stability of these dielectric charge? Are they stable at higher temperatures and during thermal cycling? And then question about scalability of the SuperQ technology.
Yes. The answer is, well, you saw the reliability. We tested to all the JEGA standards, but that's not good enough for us. We've done more than that. And that gets into the core of the IP of how we generate the negative charge. And that's done in a way so that it's immune to thermal excursions or temperatures associated with the application. So long as you can create a technology that can survive in the application, then we've been able to show that it's reliable and stable. So absolutely. I don't want to say it's thermally immune, but as a product, it meets all the qualification standards that are needed in the industry.
And any comment, David, on the scalability of this
Oh,
technology? You've already
uh,
shown
well,
that.
if you're talking about, and I addressed it a bit earlier, about being able to go to wide ranges, the answer is yes. I
Yeah.
said earlier that for 30 volts, you use a different platform. For 100, for 80 to 150 volts, you use a different platform. For 650, you use a different platform. Our technology can scale as low as 60 volts, we believe, and as high as 1200 volts. I've modeled up to 1200 volts. There's actual product you can make out of that, and it's competitive to silicon carbide. That's all in the theoretical, but for now we're focusing on 650 volts and all the way down to 100 volts today.
Yeah. So, David, we are out of time, but are you okay to stay on for a few more
I,
minutes?
I can, yes.
Okay, all right. So we'll
It is
finish these
more,
other
this is the more
questions.
beneficial portion because you get
Yes,
that's a
yeah.
scripted result, right?
Okay, question from Shrikant. How much maximum silicon area can be used for conduction? Are there any trade-offs? Uh,
Yeah, it depends on how you charge compensate, right? There are scenarios where narrower gives you a lower resistivity, as I showed some on the Infineon, but then you get into manufacturing limits, and so everything being the same, you always want a wider mesa than a narrower mesa because it's more manufacturable, and the thermal mass is greater than it is for the narrower mesa.
Shankar, hi. So Shankar has a question. How important is charge tolerance in the SuperQ device?
Oh, that's those that okay, that's a good question. Those that use charge balance, tolerance matters. And so, yes, like any superjunction structure, if you do the analysis of charge balance versus breakdown voltage, you do have a drop in voltage. And so that gets into the manufacturability, tolerance of your process and how well you control. And so, yeah, it has to be very well controlled, but it can't come at a cost that breaks the bank. And so that's where we're balancing it. So yeah, like any technology, an implant, right? You have to hold an implant to a certain percentage. Same thing with charge compensation. So we don't we're not we're also susceptible to those type of tolerance requirements.
Okay. Now the question from Phil. We chose wide bandgap semiconductors because of the peak electric field, so that we have a wide voltage range of operation. How can we get the same thing with silicon?
So, as an engineer, what I'll say is that it's great to look at just parameters like that. Oh, let's look at the electric field strength, or let's look at the band gap. End of the day, you have to make a product. So there's no point in having the world's greatest electric field if you don't have a reliable, cost-effective product. But if you could make a product, then yeah, the electric field distribution matters, and that drives the on resistance. And silicon carbide does have, as a native material, a good electric field strength. But to have it compete, now this is me as my opinion, to have it compete down to 650 is a waste of technology. I always thought that silicon carbide is better suited for north of 2000 volts. And actually, recently I saw an announcement of 10 kilovolts out of Wolfspeed, which I thought, okay, that makes sense. Now you're starting to use a technology node that is more practical in that or more useful in the application. The other one is thermal conductivity. The thermal conductivity of silicon carbide is really good. And so if you need to have an application where you have to run at 200 degrees C, then you got to use silicon carbide. And so what you try to do, you try to make products with the value proposition that is needed for the application. And so high electric field is one parameter, but you got to know where to use it. And I think, at 10 kV, absolutely, silicon carbide should be the leader there.
Okay, Shiladri, would you like to ask your question yourself? And then you can also introduce Professor Shiladri. He is part of our IIT Bombay faculty team, and he is in charge of this whole webinar program, but he was a little unwell last few days. But
Uh-huh.
Shiladri, would you like to ask your question? You can unmute and ask.
Yeah, sure. So, a fascinating talk. David, I mean, people talk of wide bandgap devices, and I'm an application person, so we
Yes,
use wide bandgap device a lot. It's
yes,
good to know that there are competitors from silicon, because traditionally power electronics training that I had was initially in the initial years, at least with silicon. So
right.
my question is, it's very interesting that you're trying to show that both the specific resistance and the switching behavior, in terms of that you showed that capacitance in EOSS plot,
Right.
uh, the super Q seems to outperform the nearest super junction device, let's say today. The
Right.
other thing that from an application perspective is important is the body diode performance sometimes. So how does
Yes.
body diode performance?
That's a very good question. Actually, I had slides, but I've got so much content, I had to take them out. I was going to address it. There's a paper that I'm going to publish in IEEE that talks about it in general and things we can do to mitigate that. Everything being the same, are the reverse recovery, for those that don't know, when you forward bias a diode, which is the body diode of the MOSFET, it injects these carriers, and to reverse block, you have to extract those carriers if you're trying to switch at high frequency. And one of the benefits of GaN is that there is no body diode. And one of the benefits of silicon carbide is that their body diode is terrible. The VF is like 3 to 4 volts. And so the question is, how does our body diode perform? As a unit cell, if you look at how we extract carriers, our extraction is more efficient than standard superjunction. We actually do have an advantage when it comes to reverse recovery, but our reverse recovery is not zero. But I took a step back and I looked at the platform, and I looked at what the industry is doing. For these higher voltage devices, dead times are at 100 nanoseconds or less. And as you get to like 50 nanoseconds and 30 nanoseconds, the impact of reverse recovery becomes a lot less for these higher voltage devices. And like I said, I've got a IEEE paper that is in process of being peer reviewed and accepted, and I'll gladly send it to you guys for reading. But my point is that the impact of reverse recovery is becoming less because of the narrower dead times. And not because what we drew. The industry wants narrower dead times because of losses. Why? Because the GaN does not have a body diode. It has an I times V product, and that in itself is a loss parameter that needs to be managed by narrowing the dead time. Same with silicon carbide. The VF drop is so high that the loss becomes prohibitive. And so once you get to 100 nanoseconds or less, and particularly for 600-volt MOSFETs, the impact of reverse recovery becomes a lot less. Actually, it's almost negligible when it comes to loss. Then it comes into the question of the ringing or the EMI. But when you get to those low levels of currents, then it's no longer a problem, because you have to realize that back when dead times were 500 nanoseconds to a microsecond, we went from MOSFETs having microcoulombs of QRR to when GaN and silicon carbide came out, had no QRR. It's like, wow, great. Now we're down to the hundreds of nanocoulombs, probably even tens of nanocoulombs, especially if you start to adjust the dead time. You get to nanocoulombs that it's still there, but it's no longer a first order impact. Switching loss, conduction loss, robustness, all these other things become a first order impact. So that's a long winded story to tell you that we do have a better body diode. We didn't make it zero, but we're in a day where the application, and along with soft switching, right? The body diode is important when you're dealing with hard switching applications. Most topologies now are just focused on soft switching, which is great because now you no longer have losses associated with the body diode or switching loss. And so to me, the industries have found good ways to manage and deal with the body diode impact. So does that
Right,
make
right.
sense?
Yeah, yeah, it does. Just one follow-up. I mean, again, from the application side. So when this wide bandgap devices came and people started using them, and they quickly found that making them work is challenging because they switch
Yes.
so fast, and you can't really retrofit them in silicon designs, right?
Right.
So looking at the performance of SuperQ, it seems closer. It seems to be switching
Oh,
faster
yeah.
and also has. So my simple question to you is, if I have a silicon design today, one of the challenges for adoption of wide bandgap is we don't have the technical expertise necessarily for system level design. So if I have to replace with SuperQ, do I need more system level expertise or at a similar level as wide bandgap?
The answer is yeah. Anytime you replace a slow switching MOSFET with a fast switching MOSFET, you're going to start excite all its parasitic elements. And yeah, our MOSFET is a high performance MOSFET. So if you have a current design that is normally being driven fairly slow or has very high loop inductance, if you put a fast switching MOSFET, you're going to have the same type of problem. So all the same challenges are there, but the caveat I'll give you is that all the methods to manage ringing and oscillations and robustness are still there for our silicon, meaning that we will be avalanche robust. Our gate drive scheme can go from 5 volts to 12 volts, so you can adjust your voltage accordingly and gate drive resistor accordingly. But if you're taking a fast switching MOSFET and you put into a TO220 package, which is very inductive, that's a disaster. It's gonna not gonna be good. That's why a lot of the industry is moving to more of these SMTs, and that was a hard lesson learned by GaN. If you recall, early on, the GaN devices were trying to replace silicon devices in TO220, didn't work out too well. And
Mhm.
so I don't want to say that we have the same story. We're working with customers, and we have plenty of applications engineers that work with our customers to try to help mitigate those risks. But fundamentally, if you put a faster switching MOSFET in a slow switching application, you're going to make other parasitic elements resurrect. And then it's up to us as application engineers or systems designers to help you guys and teach you guys how to go off and design systems so that they can be almost drop in.
Right. And just one clarification, when that in
Yeah.
that experimental measurement of the three devices that you
Yeah.
showed and the live the APEC paper. So how did you what was the gate driver side
Yeah.
of all these two devices? I mean, were you adjusting for the same switching time, or
Yes. Yes.
how
Absolutely.
was the gate resistance chosen? Because they might have different capacitances, for example.
Absolutely. No. So what we try to do is try to normalize the gate voltage and current so that we're not cheating by overdriving one and underdriving the other, right? I
Mm,
mean, we try to keep
mm,
this very fair. And so absolutely. So the GaN device, so we start off by picking devices that were close in RDS on. And that's what we did. The gate driver, we drove the GaN at 5 volts and we adjusted the gate resistor so that it had the same gate current as the two silicon devices, our device and the Infineon device. We were driving them to 9 volts or 12 volts, 9 to 12 volts, so that we can get the same RDS on, and then we were adjusting the gate resistor so they could have the same gate current, because that gate current drives switching losses, and those were the results. And those were all with surface mount packages, and meaning the surface mount MOSFETs and a QFN package and a surface mount driver, and keeping the driver really close to the MOSFETs and keeping the loop inductance low so that you don't run into these problems when you're switching fast like you do with a leaded device like a TO220. But no, absolutely, we weren't trying to cheat by making our part look better because we were driving it harder. We were absolutely trying to keep everything as well normalized as possible.
right, right. That makes sense. Thank you so much.
Okay.
Fantastic,
Yeah,
fantastic.
Thanks,
more
Landry.
details on it at APEC. If you get a chance to go to APEC, stop by, say hello.
Yeah, yeah, sure. Okay. Thank you.
Okay,
You're welcome.
so Shankar, I'll get to your question, but I have this very interesting question from earlier.
Yes.
Somebody asked, over your career, you have helped develop products that generated $1 billion in revenue. What is the single biggest manufacturing hurdle you've seen that kills a semiconductor product's ability to scale from a successful lab prototype to high volume production?
Oh, well, it's never just one problem. That's why I said earlier, as engineers, we're paid to solve problems. That's our job, right? And so it's always a multitude of problems. But you certainly have to start with an idea, and then you have to convince yourself, at least mathematically, theoretically, modeling that it's a valid idea. You know, but it starts with you thinking about the idea because usually, at least I personally, I go into a model or a simulation knowing the answer, and either the model will validate my answer, or or show that I made a mistake. And so then I try to go figure out who made the mistake. Usually me, but point is that you learn from the experience, and you say, okay, now let's take it to a prototype. Now let's take it to manufacturability. And so, there is no one hurdle. There's a multitude of hurdles, and you have to be ready to not give up because you passed one hurdle and then you found another one. You have to pause and say, okay, we failed reliability. Why did we fail? And do we have enough time and money to go off and fix it? And hopefully, if you do that right and you manage your time and you manage the risks, you end up making a product. So there's no one, and you know that very well, Ritu. I mean, you start off with, an idea that looks elegant on paper, but then bringing it to commercial success is just a long, long road. And hence why I started with that first slide that we've been doing this since 2015. We wanted to be out before COVID, but life happens, and what you do is you learn how to pivot or adjust accordingly, or you give up. And if you give up, then no one knows about your technology.
Yeah. So I'll just take this one last question from Shankar. How well do SuperQ MOSFETs parallel or connect in series?
No different than any what you've done in the past. Paralleling MOSFETs, they have more to do with how you do it and the system layout than it has to do with the MOSFET itself. If you just put the die together, they will parallel just fine. That doesn't mean that they'll operate, because if you don't make sure that your loop inductance doesn't cause oscillation, then you will get in trouble. So all the standard practices that you've done in the past with silicon in parallel MOSFETs apply here. There's no difference. But I will say that one of the biggest things that surprises that we hear from customers when we say we have the SuperQ technology, and they say, okay, well, how do I drive your MOSFET? And I say, well, what do you mean? It's like, well, again, I have to have a 5 volt. If I go to 6 volts, I break it. And silicon carbide, I have to drive it at 19 volts, and to turn it off, I got to drive it negative. So what do I have to do with your MOSFET? And we said, no, nothing. Your standard 5 volts if it's logic level, 12 volts if you want, industrial drive. That's it. Follow your standard traditional system design rules that you've done in the past, all right, or that you implement in the past. Same thing with paralleling MOSFET. This is not unique to silicon or our technology. There are some system level rules you have to follow when you parallel MOSFETs.
Excellent. Well, thank you so much, David. This was very, very good, and it's good to see a lot of questions also. And I really thank you for your time. So